Hello, my name is Ruairidh MacPhail, and I'm a master's student under Dr. Jean Hutchinson. Today, I'm going to talk about analysis of initiated rockfall trajectories and fragmentation, and specifically on how fragmentation impacts those direct trajectories. Throughout this presentation, I'm going to briefly discuss rockfall and fragmentation. I'm then going to go into the effects of fragmentation. I'll speak about video-based data and why it's integral for understanding fragmentation. I'll then go into the video rating system that we've created alongside the database of fragmental videos that we're keeping. I'll discuss this project moving forward and finally outline some expected outcomes. This is a fragmental rockfall that we're seeing here. And it's really important because it captures in real time the fragmentation event. Throughout this video, we can see the full trajectory of the rockfall pre-fragmentation, as well as the trajectory of each fragment post-fragmentation. We can see that there are a number of impacts that cause subsequent fragmentation, and it's not just a single fragmentation event. The fragmentation has caused a wider area of the road to be affected. And so this is important moving forward. It's been found that the spreading effect of fragmentation can lead to a wider section of linear infrastructure being impacted by the rockfall hazard. It's also important to note that there's a possibility that fragments will follow significantly different trajectories than an intact block. And that means that intact block modeling is not enough to understand the trajectory and the full flight path of a fragmental rockfall. While it's true that smaller particles have less mass and therefore less destructive impact power, specifically in the case of railways, Abbott et al. In 1998 found that medium-sized rocks with a dimension between 0.3 and 1 meter are of primary concern because these are the rocks that are more apt to lift rolling equipment and cause derailment. There are two broad categories of fragmentation: fragmentation along existing geologic structure and fragmentation of an intact rock block. Fragmentation along existing structure is much more common, and the number and size of fragments is dependent upon the impact angle relative to the structure and the existing plane of weakness. The lack of structure in intact rock fragmentation means that the fragment shape, size, and number are not predefined, and therefore they can vary significantly. It's important to note, however, that fragmentation research has mainly focused on a limited number of geologic settings, and that has favored sedimentary and foliated metamorphic rocks. So really, there's just a lack of understanding of intact rock fragmentation. Video-based data really is the best possible option to understand fragmentation. And that's because it shows how fragmentation occurs as long as the trajectories are visible throughout. So as long as the video is not obstructed, we can truly understand how the fragmentation has changed the trajectory of the rockfall. Without this video data, the fragmentation event may be recreated through change detection analysis, but not all impacts or fragments may be detected. The fragment shape and size is very hard to understand with change detection analysis. Whether it was a single fragmentation event or multiple fragmentation events cannot be fully understood without the real-time analysis that video-based data provides. Video-based data also allows for a complete analysis of a single fragmental event. It allows it to be broken down frame by frame. And ideally, multiple angles are used to truly determine the size and shape, as well as complete trajectory of all fragments. The main issue with video-based data is knowing where to set the camera up and how to tune it. And that's because we don't know when a rockfall will occur. However, scaling campaigns could be great video sources. And that's because rockfalls are guaranteed to occur at the planned date. We also know when the rockfall will occur, and we can set the camera up for the specific conditions of that date and time. Traffic control allows for optimal setup of camera location. The videos can be short and prioritize on events that are likely to fragment, as it is known when the rockfall will be initiated. It's also known where on the slope the rockfall will be initiated from, and it is predicted where the rockfall will land. And this all enables ideal camera angles to be set up, as well as ideal camera settings to be used. Queen's University has been working with several American departments of transportation to develop a fragmentation database. In this database, there's currently 109 videos of scaling-induced rockfall. 62 videos have a fragmentation event, and 52 of those fragmentation events are seen on screen. And this really enables long-term tracking of rockfall movement and fragmentation trends into the future. It's incredibly important to us that we capture videos with fragmentation and videos without fragmentation so that we can really understand the factors that could possibly affect why a rock fragments. As part of the development of this database, we created a video rating system. It's important for us to separate high-quality videos that can be used for detailed analysis from videos that should be used in mass analysis but might not show the complete trajectory of all fragments. And it's a 4-tiered rating system that's been created, with A having videos that are the highest quality, a complete trajectory visible, minimal camera shaking, all the way down to D having low quality videos, missing sections, or significant camera shaking. Videos in our category A are really optimal videos for research. These are high quality videos that show the complete path of the rockfall and all fragments. This includes the path of the rockfall from initiation, pre-fragmentation until the fragmentation event, captures the fragmentation event as well as the trajectory of all fragments after the fragmentation event. And this must be done with minimal camera movement to the point where the video could be stabilized. Category B videos must still show the complete trajectory of rockfall and fragments. However, there may be some movement of the camera or the rock may be partially obstructed by dust. Category C are poor quality videos, and that really means that they're missing some data. They show a fragmentation event or a complete trajectory of rockfall, but they're not enough to be useful on their own. Category D videos either do not show rockfall or have no use by themselves. Now quickly go over how one of these videos can be analyzed. In this video, there is significant camera movement, and that means that the complete trajectory of the rock, while being visible, is not visible in one frame. So frames must be stitched together to properly analyze the rockfall. In the first picture on the left, the frames are stitched together. In the right picture, all of the impact points are located. That's the impact point of the initial rockfall as well as all fragments. Finally, we can map the trajectories of the rockfall onto the photos. And this is done by following the rockfall frame by frame as it passes, and then mapping that onto the stitched images. Finally, the impact order can be labeled. In this case, it's really interesting to see that the farthest left fragment landed first. However, the farthest right fragment landed second, and the middlemost fragment landed third. So we can see that the timing of these landings is actually spread out across a wide area. From our database, we can pull 2 early trends. Firstly, the fragment shape seems to be controlled by structure and lithology, whereas the impact speed, force, and angle tend to have little effect on the shapes produced. The impact surface seems to have a significant effect on whether or not fragmentation occurs. Fragmentation has occurred only once in all of our videos on soil, and that was due to disaggregation along structure, and once on talus, in a case with a very long freefall time prior to impact. These category A videos are rare, but can enable more thorough analysis and act as model collaboration examples. Videos so far have been equally split between the various categories B, C, and D, with very few category A. Moving forward, we would like to continue expanding our fragmentation video database. We think it's incredibly important to gather rockfall data from various slopes, various climates, and various geologic conditions so that we can truly understand the myriad of factors that are impacting rockfall movement and fragmentation. We want to continue extracting shape, size, and trajectory data from all videos we currently have. And finally, we want to do a detailed analysis of fragments from a select few high-quality videos. And we want to use these videos as model collaboration tools. While this research is exciting on its own, it presents a unique opportunity to be integrated with the previous research that our group has done. This research can be combined with existing data types such as 3D point clouds and shape and size data to gain a complete understanding of a fragmental rockfall. The 3-dimensional reconstruction and lithological data can be combined to inform physical characteristics of the rockfall, including mass, allowing for computation of kinetic energy, and this can be inputted into new models. The future outcomes of this research will attempt to understand how various factors influence fragmentation, specifically whether fragmentation will occur or not. And that includes block size and shape of the rockfall, rock mass, lithology, structure, and condition, the impact energy and angle, and the slope material. This information will then be used to better understand the fragmental rockfall hazard, specifically in terms of total runout, lateral movement, and the final fragment size and shape. Some key takeaways from this presentation are that fragmentation is not well understood. Fragmental rockfalls could be more hazardous than their non-fragmental counterparts. Before and after photo datasets are not enough to fully constrain fragmentation. Videos of fragmental rockfall events are needed to better understand the contributing factors and outcomes. And finally, these videos can be used in combination with current methods such as change detection and volume reconstruction to get a complete picture of a single fragmentation event. I would like to acknowledge all members of the RGHRP, as well as specifically Mark Fish from the Washington Department of Transportation, and Matthew Tello and Ty Ortiz from the Colorado Department of Transportation for providing the videos of scaling used in this analysis. Thank you very much for your attention. I hope you have a great day.